Let's talk more about this standard cell potential. How do we know what it is? Of course, the textbook could just tell you, like it did in the previous problem, but where does that value come from? I'm going to introduce this using a different voltaic cell from the zinc-copper example from before. We're still going to use the same copper reaction for the cathode, but for the anode, we're going to use the oxidation of hydrogen gas into H+ ions in aqueous solution. The standard cell potential for this reaction, or any reaction for that matter, is the sum of the standard half cell potentials, the cell potential for the oxidation at the anode, plus the cell potential for the reduction at the cathode. So the cell potential is just the two half cell potentials added together. In the case of this particular reaction, the cell potential is positive 0.34 volts. The reason for using that hydrogen reaction at the anode is because it corresponds to the standard hydrogen electrode, which has been chosen by convention to be the reference electrode for all other cell potentials. Since a reaction can only occur with both an anode and a cathode, cell potentials can only be directly measured in pairs. Using the SHE as a reference point allows us to assign individual values for the potential of each half cell. Because it is, by definition, the reference electrode, this means that a standard hydrogen electrode has a cell potential of exactly 0 volts, whether we view it as an oxidation half reaction or reverse it and consider it as a reduction half reaction. In the case where it's paired with the copper half reaction at the cathode, and hence with the SHE as the anode, if we know the overall cell potential is positive 0.34 volts, and further that our anode oxidation potential is defined to be 0 volts, we can solve for the standard potential for the reduction of copper ions at the cathode. Solving for this reduction potential gives us a value of 0.34 volts as the standard cell potential for the reduction of copper ions to copper metal. Perhaps unsurprisingly, the cell potentials for many half reactions under standard conditions are well known. Your book has a list of some common ones, which by convention are always listed as reduction half reactions. Hence, these potentials are known as standard reduction potentials. The half reactions here are listed from most positive reduction potentials to most negative. The position of these reactions on the chart can tell us something qualitative about the substances involved. Specifically, reactions with larger reduction potentials have reactants that are stronger oxidizing agents and products that are weaker reducing agents, and vice versa, as shown by the arrows on either side of the chart. For instance, the most positive reduction potential on this chart belongs to F2 gas, fluorine gas. If you know anything about gaseous fluorine, you probably know that it reacts with almost everything else. This is because F2 is a ridiculously strong oxidizing agent. The reactants in the next few rows down, hydrogen peroxide, permanganate, chlorine, etc., are also very strong oxidizers, and hence have large reduction potentials too. Let's look at how to actually use standard reduction potentials. The key thing to remember is this: all voltaic cells consist of both a reduction and oxidation half reaction. So one half of the reaction, the reduction half reaction, will correspond to one of the reduction reactions on the previous slide. However, the oxidation half reaction will be the reverse of one of the reduction reactions, and we need to account for this. If we go back to our copper-zinc example, where zinc is oxidized and copper ions are reduced, we can determine the half cell potentials for each step. The reduction of copper ions will have a standard potential equal to the standard reduction potential in the previous slide, which is listed as positive 0.34 volts. However, for the oxidation of zinc, we need to look up the corresponding reduction reaction on the previous slide and reverse it. The reduction of zinc ions to zinc metal has a reduction potential of negative 0.76 volts, so when we reverse this reaction, the cell potential will be the same but with the opposite sign, so positive 0.76 volts. The overall reaction is then the sum of these two half reaction potentials, which adds to 1.10 volts. One thing to consider is that half cell potentials are intensive properties, meaning they don't change when we scale any of the reactions up or down by some factor. For instance, if we consider the cell formed by the reduction of silver ions at the cathode and the oxidation of copper metal to copper ions at the anode, to balance the equation, we need to double the coefficients in the reduction half reaction. This is because we always need the electrons in the reduction reaction to exactly cancel with the electrons in the oxidation half reaction. When the coefficients are doubled, the standard reduction potential for silver ions to silver metal from the previous slide, positive 0.80 volts, does not change. Since the oxidation step with copper is the opposite of the reduction version of this reaction, This half reaction now has a potential of negative 0.34 volts. Adding the two half reaction potentials together, we get positive 0.46 volts for the overall reaction. Recall earlier that we related the cell potential for a reaction to its Gibbs free energy change. Thinking back to the previous chapter, we've also related Gibbs free energy change to equilibrium and initial states for a reaction, the latter using the reaction quotient. We can combine these relationships by substituting these equations and rearranging them to arrive at what is essentially the most important equation in all of electrochemistry, the Nernst equation. The final version of this equation is circled at the bottom of the screen, where the cell potential under non-standard conditions is equal to the standard cell potential minus 0.0592 volts over n times log of Q, where we're using the base 10 log, and n is the number of moles of electrons transferred in the balanced reaction. This particular version of the equation assumes that the temperature is the standard 25 degrees C, which is pretty much universally the case for any example you'll see in this chapter. Let's try to demystify the equation a bit by looking at an example. Consider a voltaic cell that uses the reaction shown here. Copper metal and iron 3 ions in solution react to form copper 2 ions and iron 2 ions in solution. What is the cell potential for this reaction given the ion concentrations shown here? Looking at the components of the Nernst equation, the first thing we need to do is calculate E standard. Our oxidation half reaction is the oxidation of copper metal to copper ions, so we reverse the standard reduction potential of copper to get an oxidation potential of negative 0.34 volts. The listed standard reduction potential for the reduction of iron 3 to iron 2 ions is positive 0.77 volts. We need to double the coefficients in the equation to cancel the electrons in the overall reaction, but remember that this does not change the reduction potential. Adding those two half cell potentials together, we get E standard equals positive 0.43 volts. Next, we need values for N and Q. When we add the two half reactions together, the number of moles of electrons that cancel on each side is 2, so N is 2. Q can be calculated by setting up the expression for the equilibrium constant and plugging in the non-equilibrium concentrations of the ions provided in the problem. Based on the fact that there are coefficients of 2 in front of both iron ions and pure solids are excluded from the expression, you should end up with the result on the screen. Plugging in the concentrations provided on the first slide of this problem, we end up with a cell potential for these ion concentrations of positive 0.25 volts. For a reaction already at equilibrium, Q equals K and E equals 0. Making these substitutions into the Nernst equation, we can arrive at a version that expresses the standard cell potential to the equilibrium constant. E standard equals 0.0592 volts over N times log base 10 of K, assuming that the temperature is 25 degrees Celsius. Analyzing the behavior of this equation reveals a fairly intuitive result if you've followed along so far. When the equilibrium constant is greater than 1, so product favored, the standard cell potential will be positive. Likewise, if K is less than 1, so reactant favored, the standard cell potential will be negative. With this relationship established, you now have three ways to determine the value of the equilibrium constant. 1, by plugging in appropriate concentration data. 2, from thermochemical data, where natural log of K equals negative delta G standard over RT. And now 3, from electrochemical data. In this series of videos, I'm not going to cover batteries, corrosion prevention, or commercial applications of electrochemistry, although these are all interesting subjects and you can read through them in your book on your own time if you so choose. For now, though, I'm going to wrap up our coverage of electrochemistry with the subject of electrolysis and electrolytic cells. A voltaic cell uses a spontaneous chemical reaction to produce an electrical current, and an electrolytic cell is virtually the opposite. It uses an applied electrical current to effect an otherwise non-spontaneous chemical change. If we recall the relationship between delta G and cell potential, which is delta G is equal to negative N times F times E, we can ascertain that delta G and E always have opposite signs. So for a spontaneous reaction, where delta G is negative, E will be positive. This is the case for a voltaic cell, the most common examples of which are batteries. Conversely, a non-spontaneous reaction is one where delta G is positive, and hence E will be negative. These are the types of cells that require the input of electrical current to proceed, electrolytic cells. Finally, for a system already at equilibrium, both delta G and E will be 0. Since it is not spontaneous for a reaction already at equilibrium to proceed either towards reactants or products, no further energy change is possible. This is the situation reached when a battery dies. An example of a practical electrolytic cell is the electrolysis of molten sodium chloride to produce sodium metal and chlorine gas. Remember that electrolysis drives non-spontaneous reactions. You would never expect salt to decompose on its own into highly reactive sodium metal and toxic chlorine gas, but this can be accomplished with an applied electrical current. An electrolysis reaction is similar to a reaction in a voltaic cell in that reduction, in this case sodium ions to sodium metal, occurs at the cathode, and oxidation, in this case chloride ions oxidized to chlorine gas, happens at the anode, and electrons flow from the anode to the cathode. However, in electrolysis, the electron flow occurs via the output of a source of electrical power, in this example shown using a battery. The other main difference in terms of notation is that in an electrolytic cell, the anode is designated as positive and the cathode is designated as negative. This change in convention is due to the fact that the anode is hooked up to the positive terminal of the power supply or battery, while the cathode is hooked up to the negative terminal. One important electrolytic reaction that it is worth getting into the specifics of is the electrolysis of water, which is shown here. At the anode, water is oxidized to oxygen gas and H+ cations, while at the cathode, water is reduced to hydrogen gas and hydroxide ions, resulting in the overall reaction shown here. Not only is this one of the very few ways that water can be broken down into hydrogen and oxygen gases, but it's also an important factor in other electrolysis reactions that take place in aqueous solution. Typically, electrolysis reactions of substances in aqueous solution need to be carefully controlled to avoid wasting power by electrolyzing water itself. Finally, this reaction is actually at the core of a large amount of current chemical research. Hydrogen gas is a very important product for the chemical industry, as well as a potential fuel, or at least a precursor to other fuels. Current methods for producing hydrogen in bulk all have the drawback of using fossil fuels as feedstocks and producing carbon dioxide as a byproduct, which is undesirable since it's a greenhouse gas. Finding efficient ways to produce hydrogen by the electrolysis of water would be a highly desirable result, since it could avoid the production of greenhouse gases, depending on the source of electrical power used to drive the reaction. Hence, lots of research labs are currently involved in investigating ways to efficiently electrolyze water to produce hydrogen. It's a fascinating topic if you want to look into it more on your own time. Finally, let's see how we can quantitatively analyze electrolysis reactions. As you can imagine, it would be good to know how much power is required to produce a certain amount of a desired product of an electrolysis reaction, especially on industrial and commercial scales. The main considerations not covered already are these. The amount of electrical charge put into a reaction is the product of the electrical current, in amperes, or amps for short, times the time duration measured in seconds. Once we know how many coulombs of charge are used, we can use the Faraday constant to convert this to the number of moles of electrons, then use the balanced reaction equation to determine the theoretical yield. You'll see at least one or two examples of this on the homework for this chapter, and it is a topic covered on the final exam as well. And with that, we've reached the end of Chapter 19. Thanks for taking the time to watch these videos, and please let me know if you have any questions after doing so. Stay safe out there.